We look up at the night sky, we see the moon, the stars, the planets. They move in predictable ways. We feel the ground beneath our feet. We drop a ball and it falls. These things seem solid. They seem certain, and for centuries we built a picture of the universe based on these certainties. We called this picture the laws of physics. They were meant to be the absolute rules of the game. The source code for reality, but what if that picture is wrong? Not just a little bit wrong, with a few details to fill in, but fundamentally wrong. What if the rules we've discovered are just a tiny subset of a much larger, stranger rulebook? What if we're like people who have only ever seen the color blue, trying to describe a rainbow? This isn't just a late-night philosophical question, it's the central tension in physics today. The more we learn, the more we realize how little we know. The neat and tidy universe we thought we lived in has been replaced by one full of ghosts, paradoxes, and gaping holes. The story of science isn't a straight line of getting things right. It's a history of being wrong, and then a little less wrong, and then a little less wrong again. And right now, we might be at one of the biggest being wrong moments in history. To understand why, we need to go back to a time when we thought we had it all figured out. For a couple of hundred years, the universe made perfect sense. This was thanks to Isaac Newton. He gave us laws of motion and the law of universal gravitation, and they just worked. They worked for everything. Throw a rock, it followed a perfect arc predicted by Newton's math. The moon orbiting the Earth orbiting the sun, it all clicked into place. His laws were powerful, they were elegant, they suggested a universe that was like a giant clock, wind it up, and it would tick along predictably forever. Everything had a cause and an effect. If you knew the position and speed of every particle in the universe, you could, in theory, predict the entire future and know the entire past. It was a comforting thought. The universe wasn't random or chaotic, it was orderly. It was knowable. Scientists of the 18th and 19th centuries used Newton's laws to make incredible predictions. They found the planet Neptune not by seeing it, but by noticing that Uranus was wobbling in its orbit in a way it shouldn't. Something was pulling on it. They used Newton's math to calculate where that something should be, pointed a telescope at that spot, and there it was. In a new planet. It was the ultimate proof that our laws of physics were correct. We had the universe's instruction manual. The job of physicists was mostly just dotting the I's and crossing the T's. Or so they thought. But there was a crack. A tiny nagging little problem. It was the planet Mercury. According to Newton's laws, Mercury's orbit around the sun should be a stable, repeating ellipse. But it wasn't. The orbit itself was slowly rotating a little bit with each pass. It was a tiny effect, but it was measurable and it was stubborn. It refused to go away. Astronomers tried everything to explain it. Maybe there was another planet even closer to the sun pulling on Mercury. They called it Vulcan. They looked for Vulcan for decades. They never found it. The problem wasn't a missing planet. The problem was Newton. His laws, the bedrock of physics for over 2 centuries, were just a little bit wrong. That tiny error in Mercury's orbit was a clue that our entire understanding of gravity, space, and time was about to be torn down. The person who tore it down was a young patent clerk named Albert Einstein. He didn't just tweak Newton's laws. He threw them out and started over with a completely new idea. He said that space and time weren't separate, static things. They were woven together into a single fabric space-time, and he said that massive objects like the sun don't pull on other objects with a mysterious force called gravity. Instead, they warp and bend the fabric of space-time around them. Planets aren't being pulled by the sun. They are just following the straightest possible path through the curved space-time that the sun has created. Imagine a bowling ball on a trampoline. It creates a deep dip in the fabric. If you roll a marble nearby, it won't travel in a straight line. It will circle the bowling ball, caught in the curve. That's gravity. It's not a force. It's geometry. This idea, which he called general relativity, was wild. It was a complete rethinking of reality. And it made a very specific prediction. It predicted that the orbit of Mercury should wobble or precess by the exact amount that astronomers had been measuring for decades. The nagging problem was gone. Einstein's theory explained it perfectly. Newton wasn't wrong exactly. He was just incomplete. His laws were an excellent approximation for places without very strong gravity, like here on Earth. But near something as massive as the sun, you needed the new, more complete rules of relativity. Einstein's theory also predicted other strange things. That light itself could be bent by gravity. During a solar eclipse in 1919, scientists saw starlight from behind the sun bend around it, just as Einstein had predicted. His theory was confirmed. Our picture of the universe had changed forever. Space wasn't just an empty stage where things happened. It was an active participant. Time wasn't a constant clock ticking the same for everyone. It could be stretched and squeezed by gravity and speed. We use this fact every day. The GPS in your phone relies on satellites orbiting the Earth. Those satellites are moving fast, and they are in a slightly weaker gravitational field than we are on the surface. Because of this, their clocks tick just a tiny bit faster than ours. If we didn't correct for this relativistic effect, your GPS would be off by several miles within a single day. Einstein's strange new reality is built into our technology, so we replace the old laws with new ones. We went from Newton to Einstein. We were less wrong than before. For a while, it seemed like we might have the final picture. We understood the world of the very big, but at the same time, another revolution was happening. This one looked at the world of the very, very small, and it would make the universe even stranger. This was the birth of quantum mechanics. As physicists started to probe the world of atoms and the particles inside them, like electrons and photons, they found that none of the old rules applied. Not Newton's, and not even Einstein's. Down at this tiny scale, reality itself seemed to break down. Particles didn't have a definite location. An electron wasn't a tiny little ball of stuff orbiting an atom's nucleus. It was more like a cloud of probability, a region where it was likely to be. Until you looked for it, it was everywhere and nowhere at once. The very act of measuring it forced it to choose a position. This was completely alien to the old way of thinking. In the Newtonian universe, a cannonball has a definite position and a definite speed. You just have to measure it. In the quantum world, a particle can be in a superposition of many states at once. It can be spinning both clockwise and counterclockwise at the same time. It's only when you measure its spin that it settles into one state or the other. The universe, at its most fundamental level, is fuzzy and uncertain. It gets weirder. Two particles can become entangled. This means their fates are linked, no matter how far apart they are. If you measure the spin of one particle and find it spinning clockwise, you instantly know that its entangled partner, even if it's on the other side of the galaxy, is spinning counterclockwise. They are connected in a way that seems to violate the idea that nothing can travel faster than light. Einstein hated this. He called it spooky action at a distance. But experiment after experiment has shown that it's real. The universe is spooky, so by the mid-20th century, we had two sets of laws for physics. We had general relativity, the beautiful geometric theory of the very big stars, galaxies, the expansion of the universe. And we had quantum mechanics, the strange probabilistic theory of the very small atoms, particles, forces. Both of these theories are incredibly successful. They are two of the most well-tested ideas in the history of science. Relativity predicts the behavior of black holes. Quantum mechanics gives us lasers, computers, and nuclear energy. Here's the problem. They don't work together. They are written in different languages, and they describe two different kinds of reality. Relativity gives you a smooth, curved, predictable spacetime. Quantum mechanics gives you a fuzzy, twitchy, probabilistic world. If you try to use the math of relativity to describe the quantum world of a particle, you get nonsense. If you try to use the math of quantum mechanics to describe the intense gravity of a black hole, you also get nonsense. The equations break. They spit out infinities. This is the biggest clue we have that our current understanding is profoundly incomplete. We have two rulebooks for the universe, but they contradict each other. Reality should have one rulebook. The universe is one thing. A black hole is both incredibly massive, requiring relativity, and incredibly small, requiring quantum mechanics. The Big Bang, the moment the universe began, was the same. The entire universe was a point of infinite density. To understand these things, we need a single theory that can handle both the very big and the very small. We need a theory of quantum gravity. We don't have one. The fact that our two best theories of reality are incompatible is a huge sign that we are wrong. But it's not the only sign. In the last few decades, we've discovered that the universe we can see, the universe made of atoms and particles described by our theories, is only a tiny fraction of what's actually out there. The first clue came from watching galaxies spin. Galaxies are huge, spinning collections of stars. The stars on the outer edges should be moving slower than the stars closer to the center, just like the outer planets in our solar system move slower than the inner ones. This is basic gravitational physics, but when astronomers measured the speeds of these outer stars, they found they were moving way too fast. So fast, in fact, that the gravity from all the visible stars, gas, and dust in the galaxy shouldn't be nearly enough to hold them in orbit. The galaxies should be flying apart. Since they aren't flying apart, there must be something else there. Something with a lot of gravity, but something we can't see. It doesn't shine, it doesn't reflect light. It doesn't interact with matter in any way we can detect, except through its gravity. Scientists gave this mysterious stuff a name dark matter. Based on how galaxies are spinning and how they cluster together, we can calculate how much of it there must be. And the answer is staggering. There seems to be about 5 times more dark matter in the universe than all the normal matter combined. All the stars, planets, asteroids, comets, gas clouds, and people in the universe make up only about 5% of its total mass. About 25% is this invisible unknown dark matter. We know it's there. We can see its gravitational effects everywhere we look. But we have absolutely no idea what it is. It's not part of our current standard model of particle physics, which is our best theory of all the particles and forces we know about. It's something completely new. Our supposedly complete laws of physics don't account for the substance that makes up most of the matter in the universe. That's a pretty big hole, but it gets even worse. In the late 1990s, astronomers were trying to measure how fast the expansion of the universe was slowing down. Everyone assumed it must be slowing. After the Big Bang, the universe started expanding. But all the matter in it, both normal and dark, has gravity, and gravity pulls things together. So the mutual pull of all the galaxies on each other should be acting like a brake, slowing the expansion over time. The only question was, by how much? 2 separate teams set out to measure this slowdown. They looked at distant supernovae, which are exploding stars that act as a kind of standard cosmic lighthouse. By measuring how bright they appear, you can tell how far away they are. By measuring how much their light has been red-shifted, you can tell how fast they are moving away from us. What both teams found was shocking. The expansion of the universe isn't slowing down at all. It's speeding up, it's accelerating. This makes no sense. It's like throwing a ball into the air and watching it suddenly shoot upwards faster and faster. Something must be pushing everything apart. Some kind of anti-gravity force that is spread throughout space itself. It's a repulsive energy inherent in the fabric of the cosmos. We don't know what it is, so we gave it a mysterious name, dark energy. And when we calculate how much of this dark energy there must be to cause the observed acceleration, the number is even more mind-boggling than for dark matter. It turns out that dark energy makes up roughly 70% of the total energy and matter content of the universe. So let's add that up. About 5% of the universe is the stuff we know about, the stuff our laws of physics describe. The other 95% is a complete and utter mystery. 25% is dark matter, an unknown substance holding galaxies together. We are profoundly and fundamentally wrong about what the universe is made of. We are living in the dark, in more ways than one. This isn't just a small correction like Mercury's orbit. This is a complete failure of our models to describe the vast majority of existence. So where do we go from here? The main goal of fundamental physics today is to solve these massive problems. To find a single theory that unites gravity and the quantum world, and to figure out what dark matter and dark energy are. This is the search for a new revolution, a new Einstein. There are some ideas out there. One of the most famous is string theory. String theory suggests that at the most fundamental level, particles are not points. They are tiny vibrating loops of energy or strings. An electron is a string vibrating in one way. A photon is a string vibrating in another way. It's an elegant idea. All the different particles we see are just different notes played on a cosmic guitar. One of the vibrations of these strings corresponds to a particle that could transmit gravity, a graviton. So string theory naturally includes both quantum mechanics and gravity. It seems to be a candidate for that unified theory we're looking for. But there's a catch. For the math to work, string theory requires the universe to have extra dimensions. Not just the 3 dimensions of space length, width, height, and one of time that we know, but 10 or 11 dimensions in total. The other dimensions, the theory says, are curled up so small that we can't see them. Another problem is that string theory hasn't yet made a clear, testable prediction that we could verify with an experiment. It's a beautiful mathematical framework, but we don't know if it describes our actual reality. Another approach is called loop quantum gravity. This theory tries to quantize space and time itself. It suggests that the fabric of space-time isn't smooth and continuous like in Einstein's theory. Instead, it's made of tiny, discrete chunks or loops. There is a smallest possible length and a smallest possible unit of time. You can't zoom in forever. This also offers a way to unite gravity and quantum ideas, but it too is still a work in progress, facing its own set of challenges. These are just 2 of many ideas. Physicists are exploring all sorts of possibilities. Maybe gravity works differently on very large scales, and there is no dark energy. Maybe dark matter is a particle from a parallel universe that only interacts with ours through gravity. Maybe our whole understanding of space and time as fundamental is wrong. Maybe they emerge from something even deeper and more bizarre. Right now, no one knows. We are in a state of deep and profound confusion, and that's a good thing. This brings us back to the original question, are we wrong about the laws of physics? The answer is almost certainly yes, but wrong might not be the best word. A better word is incomplete. Or approximate. Think of it like a series of maps. In ancient times, our map of the world might have just been our local village and the surrounding forest. It was a useful map for day-to-day life, but it was wrong if you wanted to sail to another continent. Later, we made maps of whole countries. These maps were better, more complete, but they still had distortions. Then we made a globe, which was a much better representation of the spherical Earth. But even a globe isn't perfect. It doesn't show the mountains and valleys. It doesn't show the roads and cities. Every map is an approximation of reality, designed for a certain scale and a certain purpose. A map is not the territory. Newton's laws were a fantastic map. They were good enough to get us around our local solar system with incredible precision. They were useful for building bridges and launching cannonballs, but when you zoomed in too close to the sun, where gravity is strong, you found the map was blurry. You needed a better map. Einstein gave us that better map. General relativity. It was a more detailed map that worked at a larger scale. And quantum mechanics is like an incredibly detailed map of a single neighborhood, showing every single person and what they're doing. But it's a strange map, written in a language of probabilities. That doesn't connect to the larger scale map of relativity. And now, with dark matter and dark energy, we've discovered that our maps don't even show 95% of the territory. There are entire continents missing from our picture of the world, so being wrong in science is not a failure. It's the engine of progress. It's the discovery of a flaw in the old map that tells you there's a new, more interesting world to discover. The tiny error in Mercury's orbit was a signpost pointing towards the strange new world of curved spacetime. The fact that galaxies are spinning too fast is a signpost pointing towards a world filled with matter we can't see. The fact that the universe is accelerating its expansion is a signpost pointing towards a mysterious energy woven into the fabric of space itself. The greatest scientists are not the ones who prove the old theories right. They are the ones who find the cracks. They are the ones who show us where we are wrong, because every crack is a doorway to a deeper understanding. The goal of science is not to find the final absolute truth. The goal is to build better and better maps of reality, to become progressively less wrong over time. We live in an exciting time. We are standing at a moment of profound ignorance, which is another way of saying we are standing at the edge of profound discovery. The neat, clockwork universe of Newton is gone. The slightly less neat universe of Einstein and quantum mechanics is also showing its age. The next set of laws, the next map of reality, will have to account for the 95% of the universe we are currently blind to. Explain where space and time come from. It will have to unite the cosmos with the quantum. Whatever this new picture looks like, it will almost certainly be stranger and more wonderful than anything we can currently imagine. In decades or centuries from now, future scientists will look back at our current understanding of physics with all our dark matter and dark energy confusion, and they will smile. They will see the cracks we were just beginning to notice, and they will have their own set of laws, their own map. And they will be searching for the flaws in that map because they too will know that being wrong is the only way forward.